Hello, my name is Shailesh and today is 10th of January 2015. So today we'll solve the part B from the CSIR NET physical science exam. So part A was solved in a previous video, so if you have not seen it you can just have a look. So in part B there are 25 questions and I think you are supposed to answer about 20 of them. So let's just have a look at this. So the first problem is this. It says let R denote the position vector of a point in three-dimensional space, and R is the magnitude of this vector. So then which of the following is true? So this is easy. You just write R is equal to xx hat plus y hat plus h hat, and then you just take the divergence. So it will be del del x of the x component, del del y of the y component, and del del z of the z component. So all these three will be 1. So this is 3, and then you can take the curl, so which is equal to this determinant. Here the final row contains the x, y, z components, so which is x and y and z, and then if you just calculate it, you can see all the cross terms will be 0. Del del y of z would be 0, del del I'm sorry, this one will be del del z of y, this is 0, then this will be del y del z, that will be also 0. So all the terms will be 0, so curl of r is 0. So and this option 4 is the right one. Okay, so it's the next problem is this. It says a column vector ABA is a simultaneous eigenvector of A and B if what? So first of all you should notice that if you multiply A with this you get the same vector again. Okay, so this, because this term here and this term here, it will just permute the first and last elements, and this center one will keep be fixed. So basically if you just multiply it you get the same vector. So this is always eigenvector of A. So we can just look at this part, what happens if you multiply this with B. So if you just take this vector, multiply it with this vector, you get this A plus B twice A and A plus B. So if this is eigen vector of this one, so this has to be lambda times of ABA. So from there you get these relations. So you get A plus B equal to lambda A. That will give B equal to lambda minus 1A, and from the second one you get twice A equal to lambda B, so that will give B equal to 2 by lambda A. So these two have to be the same, so you can just write lambda minus 1 equal to 2 over lambda. So from there you get the quadratic this, and if you can factorize it, you get lambda equal to 2 or lambda equal to minus 1. So if you put lambda equal to 2 you get B equal to A, if you put lambda equal to minus 1 you get B equal to minus 2A. So this one is right, this is the correct option. Okay, so problem 3. It says what is the principal value of this integral sin 2x by x cube from minus infinity to infinity. So okay, so let's have a look at this function fz equal to e to the power twice iz over z cubes. If you just take from the imaginary part you will get this. So this function has a pole at z equal to 0. So this is a pole of order 3. So if you just calculate the residue, it will be just this half of d square by dz square into z cube of fz. So that will be e to the power twice iz, and you differentiate it twice, you get 2i out, so 2i whole square, and then you put z equal to 0, so that will be 1. So this residue will be minus 2. Okay, so now you can just take a contour. So this is the complex plane, and I take a contour from minus r to minus epsilon, and then take a loop over origin, and then again go to r, and then come back to minus r in a circle. So and now I try to evaluate the integral on this. So first one is minus r to minus epsilon, and then it's this over this curve gamma 1, so which are right here, and then my epsilon to r, which is this, and then on the bigger circle is this one. So here now I take the limits, r going to infinity and epsilon going to 0. So in this limit, this one will go to 0 because you have this r cubed, and this numerator will remain finite. So fz will go to 0 if the radius becomes too large, and here we can just calculate the residue. Okay, so once you take the limit, you get these two will combine, you get minus infinity to infinity fz dz, and here the residue will be 2 pi I times of this, and you are going in a clockwise direction. so there will be a minus times here, and since it's just half the loop, so you get half of that. So once you do this, after that you can put this z equal to x plus iy, but on this real line y is 0. So once you put this here, you get e to the power twice ix over x cubed dx plus 2 pi I. This one is 0. So now you can just equate the imaginary parts. So you get this sin 2x by x cubed dx plus 2 pi equal to 0. So this integral has to be minus 2 pi. Okay, but here I have some doubts, because if you look at this function near origin, it will take positive values, arbitrarily large positive values. So if you just evaluate this integral, I think it should give a positive value and not a negative. So it's possible that I made a mistake in sign somewhere, or but I checked a few times, I didn't see any mistake. Also, maybe it's possible that the integral is divergent. So maybe you can just have a look at this and see if you find something wrong here. Okay, so now we move on to the next problem. It says the Laurent series expansion of the function fz equal to e to the power z plus e to the power 1 over z about z equal to 0 is given by what? So okay, so e to the power z, you can write this z to the power n by n factorial and then summation, and so similarly e to the power 1 by z, you can write this 1 by z to the power n by n factorial. So this function, of course, it blows up at this one at 0, and this one you should avoid infinity. So if you look at the sum, these two sums seem alright. This seems a little bit weird, these two, but if you just write z to the power minus n, then you can take the summation from minus infinity to infinity, and you can write it this way. But then you will get these factorials as negative, so that seems a little bit weird. So you can just simply avoid these option 1 and 4. They are not right, so you just have to choose between 2 and 3. So in 2, the limits it says it's valid only for within the unit circle 1, and it says this is valid at all points except 0 and infinity. So if you take z equal to 2, even then this series holds. Okay, so it's still finite and it converges. So this option 3 has to be the right one. Okay, so it's basically valid at all the points except 0 and infinity. Okay, so the next one, it says two independent random variables m and n, which can take the integer values 0, 1, 2 till infinity, follow the Poisson distribution with mean values mu and nu. Then which of the following is true? So the probability distribution of L, which is m plus n, this is a binomial distribution, which is not correct, of course, because sum of two Poissons is not a binomial distribution. Poisson distribution itself is some kind of a limit of a binomial. So the second one says the random variable r is m minus 1, that follows Poisson distribution. That also is, of course, no. And the variance of the random variable m plus n is equal to mu plus nu, and then it says the mean value of random variable r equal to m minus 1 is equal to 0. So the mean value of the sum or the difference of two random variables is basically the sum of the two random variables, or the difference. So here it will be 0 if only if m and n are the same. So this is also, of course, not right. So let's just check this option 3 a little bit more carefully. So it says the variance of a random variable L is which is m plus n is equal to mu plus nu. So the variance of m plus n will be equal to variance of m plus variance of n, but here it says the mean values are mu and nu. So this seems a little bit incorrect, but then you should notice that for the Poisson distribution, the mean values and the variance are same. So if it has a mean value of mu, the variance is also mu, and if the mean value is nu, the variance will also be nu. So this option is right. This is the right option. Okay, so this problem 6, this is quite simple. It says the equation of motion of a system described by the time dependent Lagrangian this is what? So you just apply this equations of motion. So this is del L x dot ddt and minus del L del x is 0. You just put the values. So if you take with respect to x dot, you will just have this term, and if you just take with respect to x, you will just have this term. and you just differentiate this one again, you get this, and you can just take e to the power minus e to the power gamma t, just common, and you just take it out. So what remains is basically this. So this is the right option. So next problem, it says a particle of mass m moving in a potential Vx, which is minus half ax square plus 1/4 of bx to the power 4, and AB are constant. So the frequency of small oscillations about a point of stable equilibrium is what? So if you just draw the graph of this, you can see that it will look a little bit like this. So near the origin it will follow this one, and away from origin it will be this bx to the power 4. So here it will be an inverted parabola because of the minus sign. So one of the point of stable equilibrium is this x naught, and you have to find oscillations about that. So the normal way to do it is, first you find x naught, you put dv dx equal to 0, and you find this value, and then you do a Taylor series and expansion around this point, and then you basically take the derivative of potential and equate it to force, and then you get acceleration from that, and then you write acceleration is minus omega naught square by x, and then from there you get omega. So you can do that, or you can just do a small trick. So the point is that near this point the expansion will be still follow this one, the first order term will still be half ax square. So only that here it is an inverted parabola, and here it will the parabola sign will be reversed. So if you take a small displacement around this x naught, the v of s will be just this. So you can check this, you can actually do a Taylor series expansion, and you can see that it is actually this. But if you just remember it, that if you just take a Taylor series expansion about in between two polynomial terms, one is it is x square this side and x4 this side, for the small range it will just follow still the smaller power here. So you get you just write this, and from there you get the force, which is minus s, and then you get the acceleration, which is minus a by m. So omega square is a by m, so omega will be under root a by m. So this should be right option. And also you can just do a normal Taylor series expansion about this, find x naught, and then find a Taylor series expansion, and then do it. You will basically end up with the same thing. So you can just try doing that and see if you get the same result. Okay, so next problem, it says the radius of Earth is approximately this 6,400. So the height h at which the acceleration due to Earth's gravity differs from g from Earth's surface by approximately 1% is what? So this is simple. So at the surface, this is the value of gravity. At a height h, it will be r plus h. So it's this. The difference will be 1%. So it's 1% of the value of gravity at the surface. So it's this one, and now you can just evaluate this. So just GM will cancel out, and then you can take this term to this side and this term to this side, and basically you will have this, and just r square you can just bring it on the other side. So you will just get this one, and you can write this as 1 plus h over r whole square is this. So this side you can write 1 plus 1 over 99 to the power half, and then you can do a binomial expansion and just return the first term. The higher order terms will be very small. So, and then you can just equate h by r equal to this, which is approximately 6,400 by 200. 99 is approximately 100, so you'll get 32. So this is the right one. Okay, so this one's okay. So it says that according to the special theory of relativity, the speed v of a free particle of mass m and total energy is what? So you have this relation equal to mc square. So here m is basically the moving mass. So you can just change this and write m naught by 1 minus v square by c square, and you just simplify this expression. You can just bring this one to other side, square it, and you will get this. So, and if you just take a square root, you basically get this term here. So you just take a square root of this and bring c to the other side, you get this. So this option 3 has to be right. So here you should note that m is probably not the moving mass, it has to be the rest mass, otherwise you should get this relation. Okay, next one is this. It says a charged particle moves in a helical path under the influence of a constant magnetic field. The initial velocity is such that the component along the magnetic field is twice the component in the plane normal to the magnetic field. So the ratio L by R of the pitch L to radius of R of the helical path is what? So this is the helical path. It has a diameter 2R and the pitch is L. Okay, so basically it's that means the time in the time that the particle moves one full revolution, it also moves a height of L. So the field of course has to be in this direction, and of course it's also given that if the velocity perpendicular to B is v, then in the direction parallel to that it's double of that, so this should be 2v. So now you can get, for the circular motion you can just write mv square by r is equal to the force, that's qvb, so you get the velocity here. So from there you can calculate the time period of one revolution, so it's 2 pi r over v, so you can just put the value of v, you get this. And also in this time t moves a distance L along the direction of b with a velocity 2v, so you also have L is equal to, or t is equal to L over twice v. So you can just put the value of v again here, you get this, and then you can equate these two and find this ratio. So basically 2 pi m over qb is equal to this, so, and from there if you just simplify you get 2 pi is equal to L over twice r. So you get L by r is equal to 4 pi. So this is the right answer. Okay, so next problem, it says a parallel beam of light of wavelength lambda is incident normally on a thin polymer film with air on both sides. The film has a refractive index n greater than 1, so the second order bright fringes can be observed in reflection when the thickness of the film is what? So for reflection, if you notice the condition for maxima is 2 into n into d is m plus half lambda, so there is an extra term half which is not there if you consider the transmission case. So this half lambda term is there because when the light reflects back from the film there is a phase change of pi, so this denotes that. So if you don't write this term, you will get a wrong answer. So this you have to be a little bit careful. So here d is the thickness of film, n is the refractive index, and m can take integer values. So the allowed thickness that you have, if you just put m equal to 0, 1, 2, 3, etc., you get this d equal to lambda by 4n, 3 lambda by 4n, etc., and so on. So here two options are given, lambda by 4 and 3 lambda by 4n. So which one to choose? So if you have lambda by 4n, you basically get all the orders. So if you just take 3 lambda by 4n, some orders will be missing. So but since this one has all the orders, so the first order is also here. So without doing much calculation, you can just tick this one. This should be right. And also you can calculate actually for this 3 lambda by 4n, the first order should probably be missing. Only the second order will be there. I mean the second order will be missing. So the first order will probably be there, and then the third order. Okay. Okay. So the next problem is this. So it says there is a solid sphere of radius r, and it has a charge density which is given by this, and r is the radial coordinate, rho naught a are positive constant. So the magnitude of electric field at r equal to r over 2 is 1.25 times that of r equal to r. Then what is the value of a? So you have this relation, E dot ds is equal to the q enclosed. There is a term divided by epsilon naught, so but you can still write proportional. So you just apply this. So in first case, when you consider a sphere of radius r by 2, so the field at the surface is E r by 2, and then take a ds, as the surface area will be 4 pi r by 2 whole square. And when you consider a sphere of radius r, you get this term as this integral E dot ds will be E r into 4 pi r square. So this is the q enclosed in one case is this. So you take a small shell of radius r and thickness dr, so its volume is basically 4 pi r square dr, and the charge density is this one, rho naught 1 minus a r over r. So this is the total charge enclosed. So you integrate it from 0 to r over 2, and in the second case you just integrate it from 0 to r. So now you can just calculate and put the values. Here 4 pi will cancel out, rho naught will cancel out, and then you will integrate it. So here it will be r squared dr, so that will be r cubed, and then this will be r cubed dr, so this will be r to the power 4. So you just put all these values correctly here, and on the left hand side, so er by 2 by er is 1.25, so that's 5 by 4, and this second factor becomes 1 by 4, which becomes this basically. This 16 you take it to the numerator, and you get this 2 by 3 minus a by 4 by 1 by 3 minus a by 4 is 5, so which simplifies to this. So if you just put a equal to 1, you basically get 5, so this denominator will be 1, this will be 5 if a equal to 1, so a has to be equal to 1. So in this problem you just have to do this evaluation properly and see that you don't miss out a factor of half or something like that, otherwise you will just get a wrong answer. Okay, so the next one is this. It says the electrostatic lines of force due to a system of 4-point charges is sketched below. So at a large distance r, the leading asymptotic behavior of electrostatic potential is proportional to what? R minus 1, r minus 2, or r minus 3. So if you just look at this charge distribution, what does it indicate? So let's say here there is a positive charge, so the field lines are going here, so this will be minus. So from there it's again going here, so this has to be plus, and if this is plus, this again has to be minus. So you have alternating 4 charges, and they also have to be equal in magnitude because the field is symmetric. So this system is basically that of a quadrupole. Okay, so this is called a quadrupole. And if you just remember, the expansion of field in terms of its moments. So the first term goes as q total by r, the second term is the dipole moment by r square, the third is quadrupole moment over r cube, and so on. So in this case the total charge is 0 because of plus minus, and they are all equal magnitude, so this is 0. The net dipole moment is also 0 because this dipole here and this dipole here will cancel each other out. Only net quadrupole moment remains. So Vr in the first order will go as r cube. So and this is the right one. Okay, so next problem is this. It says suppose a Hamiltonian of a conservative system in classical mechanics is this: h equal to omega xp, where omega is a constant and xp are position and momentum respectively. The corresponding Hamiltonian in quantum mechanics and coordinate representation is what? So this is basically quite simple. You just replace x and p by the quantum operators. So you just replace this by x operator, this by p operator, and you should get the answer. So h you can write this xp, but since these operators do not commute, so you write the average of xp and px. So you replace this by half of xp plus px, where x basically will mean multiplying by x and p is minus I h cross del x. So this is the answer. So if you just do a h psi here, so this will be p psi, this will be x psi, and then you evaluate this. So this will be minus I h cross del x, this will be just x into psi, this is just normal multiplication. And this one, now you operate this with the operator x, it will just multiply, and this you operate with operator p, so it will be del x of x into psi. So you differentiate this, you get these two terms, and this you can just take psi out and you get twice x del x plus 1. So then you can bring 2 inside, you get x del x plus half. So this h has to be this one. Okay, so h is this. Okay, so next problem, it says let psi 1 and psi 2 denote the normalized eigenstates of a particle with energy eigenvalues E1 and E2 respectively, with E2 greater than E1. So at t equal to 0, the particle is prepared in a state of this psi 1 plus psi 2 over root 2, and the shortest time t at which this psi will become orthogonal to the initial state is what? So initially it's prepared at this state. So if you just look at its time evolution, so it will be psi 1 you multiply it basically with this term, this energy term, and with the psi 2 you multiply it with the corresponding E2 term. So this is the time evolution. At any time t, this will be the state. So So at some point it will be orthogonal to this. So if you take a dot product with the initial state, that should be 0. So once you do that, you will get the cross terms. They will be 0 because these are eigenstates, so they will be orthogonal. And also the same terms, you will have psi 1 into psi 1 star. They will be unity. So all those will be just 1. So you just get this term, and then you can take E1 out, and this half term you can just basically forget. So this has to be 0. So this has to be -1. So that means you should have this as minus I pi. So this one has to be pi. Okay, E2 minus E1 by h cross t is pi. So then you can get t is pi h cross pi. E2 minus E1. So this should be the answer. Okay, the next one, it says consider a normalized wave function of this a1 psi 1 1 plus a2 psi 1 0 plus a3 psi 1 1 minus 1, where psi lm is a simultaneous normalized eigenfunction of angular momentum L square and Lz with these eigenvalues, and it says phi, which is this combination of this, is an eigenfunction of operator Lx for what values of a. So if you just remember, this Lx operator is basically this. You have 4 ones going there, and if you find the eigenvector of this, I'm not doing it, but it's simple. You can just do it. You will get this factor, vector 1 by root 2, 1 by root 2, and you just normalize it. You get this. Okay, so you get 1 by 2, 1 by root 2, and 1 by 2. And so if you write a wave function phi in terms of these basis vectors, you will get this phi equal to half of 1 0 0 plus 1 by root 2 0 1 0 plus half of 0 0 1. So you can see that 1 0 0 basically corresponds to psi 1 1. 0 1 0 will be psi 1 0, and this will be psi 1 minus 1. So it's basically this. So from here you can see a1 is 1 by 2, a2 is 1 by root 2, a3 is 1 by 2. So it's this one is the right one, option 2. Okay, so it says x and p denote respectively the coordinate and momentum operator satisfying this commutation relation xp equal to I. H bar they have put it to 1, and then what is the value of this commutator? So this is there is a little bit of calculation unless you know some tricks. So you have this xp minus px is I, and you find the commutator of this. So the first term will be xp e to the power minus p. So if you just expand e to the power minus p, you can just write it as this term. Here what I would like to do is I would like to bring x on the other side, so that I can bring that to this side, and then you will have the commutator and you will have the resultant value in here. So I just take this term xp to the power x minus 1, and you just take these two terms together, x into p. You just pull out one p from this side, and since you have this xp minus px is I, so you can write xp is equal to I plus px. So you get this to the power p to the power k, so you get ip to the power k, and then x has gone a little bit inside, so 1p is on the other side, and then you have p to the power k on the other side. So now I can continue this process again. I can just put again take 1p from the other side and just put it together here, and you again write this one as I plus px, so you get this. So similarly, if you just continue doing this, the terms on this side will be increasing, and this the power of this will increase, and finally you will get this k plus 1 I p to the power k plus p to the power k plus 1 into x. So just please verify you get this, and so now you can just substitute this value back here. You get this. So this term is basically the other part of the commutator. So if you just bring this to the other side, you get this commutator here, and the value of this will be this one. So this commutator x p to the power minus p will be just this first term here, and now you just try to basically evaluate this. So this part I p to the power k will be I e to the power minus p. Please verify that this is right. And this one I've just tried to put one p outside the bracket, and I'll write this as a derivative of p to the power k. Then I can just take ddp outside, and you basically have p to the power k here. So this will be ip into ddp of p to the power e to the power minus p, this. So once we do that, you get minus ip square and e to the power minus p. So this answer seems to be right. So please verify that I have done all the steps correctly, and this should be the answer. Okay, so there is just some calculation in this. Maybe if you know some tricks, you can do it faster. In these kind of problems, it's always possible that you miss out some factor, or you don't multiply properly, or something like that. You have to be a little bit careful. Okay, so next problem is this. It says the pressure P of a fluid is related to its density, number density rho, by the equation of state. This. So P is basically this, where A, B are constant. So initial volume of the fluid is V naught. The work done on the system when it's compressed, so as to increase the number density from rho naught to rho naught, is what? So work done is basically this. It's integral of P dV. It's, the work done by the system is integral P dV. So work done on the system will be minus of that. So I just try to evaluate this one. So rho is the number density, so you can write V is equal to N over rho. So you get dV is this. And now you just put the values of P and dV here. You get this one. And the initial value of rho is rho naught. Final value is twice of rho naught. And you can again write V naught into rho naught, because this N is a constant here. And now you basically just do this integral, and you'll get a log 2 term here, and you get a rho term here. So this is the right one, option 4. Okay. So next problem is this. It says the Hamiltonian of a classical particle moving in one dimension is this: P square by 2m plus alpha q to the power 4. Where alpha is a positive constant and pq are momentum and position respectively, and it's given that the total energy E is less than or equal to E naught. So the available volume of the phase space depends on E0 as what. So once you put, you just try to evaluate the curve by putting the energy E naught. You just do this, and you can see that it will be a closed curve, and it will be symmetric, of course, about x and q, because these are all even functions. Also you can see that derivative here will be 0, here it will be infinite, things like that. So the volume of phase space will be equal to volume of inside this area, because the particle has energy E less than E naught, so it will remain inside this. Okay, so the volume is the area of this one, so it's 4 times the area of one quadrant. So if you just take from 0 to q naught, which is the maximum it can take. So you just try to evaluate this. And basically you just write P as the other terms. Take 2m twice m on the other side, alpha q to the power 4 on the other side, and you just take a square root, you get this. And now I would like to put this one as sine square theta. Okay, so this one I just put sine square theta. You will again get e to the power 1 by 4 as a constant. And after that, this integral will just be an integral of sine theta, where theta will go from basically pi by 2 to 0. So that will be a constant term, and you can see that you get a root e naught here, and then you will again get a e to the power 1 by 4. So the volume will basically depend on e to the power 3 by 4. So you can just tick this one here. This option 1 is the right one. So here you don't have to basically calculate all the area. So just once you see that volume depends on e to the power 3 by 4, you can just check this option. Okay, so next problem is this. It says an ideal Bose gas is confined inside a container which is connected to a particle reservoir. Each particle can occupy a discrete set of single particle quantum states. So if the probability that a particular quantum state is unoccupied is 0.1, then the average number of bosons in that state is what? So it's connected to a particle reservoir, so it means the number of particles in the box can go from 0 to infinity, anything. Okay, so the probability that there are n particles in energy state E is basically given by this. It's k into e to the power minus n beta E, where k is basically a constant. So it's given that the probability that the state is unoccupied is 0.1. So if n is 0, then you get the probability as 0.1. So if you just put n equal to 0 here, you should get 0.1. From there you get k equal to 1/10. So that's one value. And now the sum of probabilities over all the particles from 0 to infinity has to be 1. So if you calculate this, you get e to the power minus beta epsilon as 9 by 10. So in normal, if you have this, if you do this both statistics, here the number of particles is fixed, but in this one it can go to infinity. Okay, so from there you get this term e to the power minus beta is 9 over 10, and also if you remember the expected value, this is photon statistics, it's basically 1 over e to the power beta e minus 1. So there you can just put the value and you get the answer. So even if you don't know that, you can just try to evaluate the expected number of particles. It's n into the probability over the total probability and sum. So this will be 1, and you just try to evaluate this sum, or here I can just write this one as a derivative of log of this. You get this one, and again you can evaluate this this summation easily. So once you do that, you just put the value of this e to the power minus beta is 9 by 10. From there you get the expected number of particles as 9. So this option 2 is the right one. Okay, so next one is this. As this is a simple problem. It says in low density oxygen gas at low temperature, only translational and rotational modes of molecules are excited. So the specific heat of per molecule of the gas is what? So basically it has 3 translational degrees of motion, and it has degrees of freedom, and it has 2 rotational degrees of freedom. So because it's a diatomic particle, so along the line which joins these 2 molecules, the moment of inertia is 0, so you will basically avoid that, and it can rotate in other 2 directions. So the number of degrees of freedom is 5. So and each degree contributes half kT, so you have 5 by 2 ks the specific heat. Okay, so next is the problem on electronics. It says consider the amplifier circuit comprising of 2 op-amps, this and this. It says the source signal has an impedance of 50 kilo ohm. So which option is right? So it basically talks of why this A1 is required or why it should not be required. So if you look at this this circuit A1, the output is basically directly short circuited to this negative terminal. So if you just can recall that this is called a follower circuit. Okay, and the reason why this is put in the circuit is because it's basically separates the 2 halves of the circuit, and if there is any noise or any fluctuation in this part, it will not affect the other half. So it's basically adds to the stability. It has a gain of 1, and it's non-inverting, of course. So if you look at all the options, this option 1 and 2 is obviously wrong. This is not the reason why you put this forward circuit. It has nothing to do with the values of these two resistors. Also, this option 4 is also right. Is also wrong, because it says the A1 is required if the output has to follow the phase of input signal. That is also wrong, because this is non-inverting, so the phase does not change. Even if you remove it, it will still have the same phase. So 1, 2 and 4 are wrong, so option 3 has to be right. So it says A1 can be eliminated from the circuit without affecting the overall gain. So that is right, because it has a gain of 1, so even if you remove it, the gain will not change. But of course it's not advisable to remove it, because then the system might become a little bit unstable, but still option 3 is the right one. Okay, so then next is again electronics problem. It says the current in a diode is given by this. It's V minus 0.7 by 500 if the applied voltage is greater than 0.7, and it's 0 if voltage is less than 0.7. And this is the circuit. So it says what is the current I in the circuit. So here you can apply this Kirchhoff's law, and normally we have to decide whether I should use this formula or this one, but in all these options I can see that current is non-zero, so basically I can just drop this and I can just apply this one. So if the voltage drop across the diode is V, and then the voltage drop across this resistor is 10 minus V, so the current here and current here has to be same. So this V minus 0.7 by 500, and the current in the resistor is this voltage by the resistance, that's 1000. So from there you get V equal to 3.8, and then you can basically just plug it back in here to get the current. So current is 10 minus 3.8 by 1000, so this is 6.2, so it is 6.2 milliamps. So this option 3 is the right one. Okay, so next is this. It says a junction is made between a metal of work function Wm and doped semiconductor with Ws, and where Wm is greater than Ws. So if the electric field at the interface has to be increased by a factor of 3, and then the dopant concentration of semiconductor would have to be increased by what factor? Okay, so here we have a junction between a metal and a semiconductor, and if Wm is greater than Ws, then what happens is that the electrons from the semiconductor is basically pulled into the metal surface, and then that causes a local electric field, and that produces a local electric field at the node. So this is called Schottky junction. So if you just remember the formula, the formula for electric field is given by this. So here E is the electronic charge and D is the dopant concentration, etc. So from there, if you just remember that the electric field basically goes as the square root of the dopant concentration, you get the answer. So if you want to increase the electric field 3 times, this has to increase 9 times. So this option 1 is the right one. Okay, so this is the last problem, and it's simple. So let's see. So it says in a measurement of viscous drag force, the force is found to be proportional to v to the power 1 by 3, where v is the measured volume of each particle. If v is measured to be 30 mm cube with an uncertainty of 2.7 mm cube, the resulting relative percentage uncertainty in the measured force is what? So first we can write measured force as proportionality constant into v to the power 1 by 3. So now you calculate the relative uncertainty. So here the error is v plus delta v minus fv over fv. So here you can just write k into v plus delta v. K will cancel out, so you just try to evaluate this. So you divide it by v everywhere, you get this 1 plus delta v by v and minus 1, and then you expand this with binomial theorem, and you just return to the first order, because the second order you can see that it will go as 1 by 100 whole square, so that will be very small. So it's 1/3 of this, so it's 1/3 of 2.7 by 30, that's 0.03. So this is the relative uncertainty. So the percentage uncertainty will be 100 times this, so it will be 3. Okay, so this was the last problem, and we have solved part B from this NET physical science paper. So hope you enjoyed it, and if you have anything to say, please feel free. So thank you very much, and I'll see you next time. Bye.